Okay, so I'm gonna explain you something about the ICOS Curve. And ICOS Curve is an application which is meant as a kind of explanation why, for the ICOS, for the atmosphere component specifically, we do our measurements and what is the result of that. So I'm gonna present this, but of course the work is done by not me, but all these people in the ICOS research infrastructure. So too many to put on one slide, but there's a few hundred people involved in all this exercise, and I thank you all for this marvelous work. So the ICOS curve, I'm going to explain a bit more later, but there are already kind of similar systems on the global scale, while the ICOS curve is more, let's say, on the continental scale. There is the the WMO GAW, the World Meteorological Organization Global Atmosphere Watch. They annually, around October, November, they publish the atmospheric growth rate for the most important greenhouse gases in the Greenhouse Gas Bulletin. And at the start of each year, also NOAA gives a number for the atmospheric growth rates of the greenhouse gases, the major greenhouse gases. So this is all based on a global network of which also ICOS is part. I can show you where we are, of course. So this is about where our measurement stations in Europe are, and they contribute to this global effort. And of course, it's important to know where, how the greenhouse gas concentrations are developing to know what we can expect for climate change and whether our abatement of greenhouse gas emissions is working or not, or whether, for example, natural ecosystems are responding to the global warming by taking up more or taking up less CO2, dependent on region. So this is where all this kind of information go. We want to listen to the atmosphere, and we'll come back to that a bit more on how we can listen to the atmosphere, what the atmosphere can tell us about the fate of greenhouse gases that we emit and we influence through climate change and through our land use, how these work. So you can all go to this Curve application. It's an interactive application, and the purpose of it is to show all the observations we have from the ICOS atmosphere. So you see on the right, you see all the stations we have in the Northern Hemisphere, and in the application, show you, I hope you see my mouse, you can set a date range, you can select one or more stations, you can add one or more global numbers. You can select whether you want to see CO2, methane, or nitrous oxide. You can change some colors and percentiles. I will go a bit through what you can see actually in the app directly, just as a picture without any words. But first of all, the ICOS curve is, as I said, it's regional for Northwestern Europe. It will also detect changes in the Northern Hemisphere earlier than the background network that I showed you from NOAA and from the WMO Global Atmosphere Watch. It will deliver growth rate estimates with a minimum delay because in ICOS we can have this near real-time data. So with 1 day delay, we can already, on the 1st of January 2026, we can already say what was the growth rate according to our network in 2025. It dynamically adapts to the data updates like scale updates. So anytime through a station, when station changes data through the atmosphere thematic center, this will dynamically be taken up each day into the application and be calculated through and be put into the numbers. It's scalable. We could as well take in global data from other networks when this data is available. It's fully interactive. It demonstrates for the audience the variability of the greenhouse gas signal and also demonstrates the quality, compatibility of the atmospheric network. It works for carbon dioxide, methane, and nitrous oxide, together 90% of the greenhouse gas warming potential of anthropogenically influenced increased atmospheric composition of these gases. But in the talk here, I will focus on carbon dioxide to make things not too complicated and to need too many words. So in the end, the Curve app boils down to one number, but there's a lot of complexity behind it, and that is the purpose of the curve tool, that we show all the complexity behind this one single number, and to also pull out, because that is the information that scientists want to pull out from this, not this single number that is interesting for policymakers and also for the general public. But what we are actually interested in is all these details, all this information behind it in the network that we want to use. But one number is the atmospheric growth rate. So here for the two most recent years, 2024, 2025, you see the numbers from the global systems, which are more or less compatible within the uncertainty, also with the ICOS curve for 2024. But we see some changes in 2025. So the WMO is only available in 6 months from now, but NOAA has already a number 2.12, which is significantly different from the growth rate that we have from the ICOS curve 3.10. But of course, when you add up all things and watch over longer time series, so that's also why we have the column on the right here with 2000 to 2024, you see that they provide actually exactly the same number, because in the end, CO2 has a long lifetime in the atmosphere, and in the end, everything gets mixed on the northern hemisphere and between the northern and the southern hemisphere. So in the end, the CO2 can't hide, and we will get with all the measurements, as long as we are all on the same accurate scale to the same number, which we demonstrably do. But for a year, there can be differences, because there is a bit of the CO2 is still hiding, or still a bit of the update of CO2 can still hide in the southern hemisphere or in the northern hemisphere. So the global network sees something a bit differently, more mixed than what we see in the ICOS curve. So we can explain that there will be this kind of variability, but that is exactly the kind of variability which is interesting for the models, and to see what actually is causing that and what is changing in the atmosphere. So you can boil it down to one number. You can also boil down the whole network measurements, all the millions of observations, into one single median of the concentration, the monthly median concentration of the network, which is this curve. If we start at 2017, which is the year when ICOS has really the labeled stations, and the first stations started to bring in labeled data into the Atmosphere Thematic Center, and through the Carbon Portal, all available with minimal delay. When we look at the whole network, that is, then you get this curve, which is the default curve when you open the Curve app, is where you show a bit of this variability at the ICOS station. So we have the median, we also have a band of variability of 50% of the stations and of 90%. You can change these numbers if you want. And in the plot, you can add also the global average, and you can see that we follow exactly the same global trend, because we are so accurate and precise. But the variability is much higher, and also we see a much bigger signal of the biogenic and the anthropogenic emissions. So when the curve of the ICOS stations go below the global background, that means that we pick up a signal from the biosphere, the uptake of the biosphere in the summer. And when the curve goes higher, then we see a signal from respiration in the winter from the ecosystems, and also fossil fuel emission, related emissions of CO2, which is a huge signal in our densely populated Europe. And this is also a bit similar from what we see from the Mauna Loa station. So a single station, you can get from this single station, if it's not contaminated by local sources, you can also get this global growth rate pretty accurately if you have more time series over a longer period. But you see also local influences. So even in Mauna Loa, you see influences of local CO2 emissions from respiration in the environment of the Hawaii island, and also uptake by the ocean, and also a seasonal shift compared to the global average. So I'm doing too much. And then we can add also in the plot one or more ICOS stations. So I put here Jungfraujoch, which is the blue line, which is at the lower envelope, so the lower 10% of the ICOS data, which is a nice background signal. And then one example of a high concentration profile is for the CO2 from Cabauw Tower, which is close to sources and also close to uptake from grasslands. You can see also that even this curve, you can see a signal in the summertime from the uptake of the biosphere compared to the, but it's very small. And that is also why we need this accuracy and precision, because if we want to catch in the midst of all these variability signals from different sources and sinks, then you need to have this really on top of this high background of more than 400 ppm. You need to have this high precision accuracy of zero point 0.1 ppm or better even for the whole network. And we will discuss a bit more of that now. You can also show the whole network. So you can see that there are some stations like Karlsruhe and Jülich, which are really above the high 90%, and some stations which are really low, like the stations in the polar regions, which are really low and have a low variability. So this is, of course, why we show this curve, because this is much easier to follow than a curve where all this information is included. As a human being, you can't do much with this kind of spaghetti. You can cook it and eat it, but you can't understand it. So what we need to do is to use models to interpret all these signals which are in this monthly variability. And actually it's worse, because for example, we see here this Jungfrau Joch series again. You see the monthly plot still there below. You see the monthly median of the network, but you also see the hourly observation, which has much more variability because there's upslope and downslope winds. So sometimes from the valley, emissions from CO2 are brought up to the measurement station, and sometimes there's stratospheric intrusion, and then you get very low concentrations. So there's all kinds of variability in that data that we gives information on what is happening in the carbon cycle, but it needs a very good model to tease that out. Until now, I showed only the 2017 to now data, but our data goes back further. So the first station, Schauinsland in Germany, started to produce CO2 accurate data since 1972. So this is the whole time series. You see the plot again for the whole network, the blue line. And on top of that, as soon as we have more stations, you get information on the variability of the signal. So here it says stations like Hetschachal and Cabauw came in the year 2000 with the projects Europe, etc. We started to add more and more stations until then in 2017 we came with the current network. We started to have this 40 station network in Europe. And in the end, what we do with the curve app and what we show is that we boil down all this information into one number, the 1.89 ppm over 1972 to 2025. And then recently, unfortunately, still an increase of 310 ppm per year as a network annual trend in 2025. And we don't really see a sign yet of decreasing, although from year to year, as you saw in the numbers from NOAA and Global Atmosphere Watch, there is this variability of about 1 ppm per year in this trend, due to all kinds of natural variability, ENSO variability, etc. So zooming in, you can also zoom in. You can look at the most recent 4 months and see that we calculate always until the middle of the previous month. So as soon as it is the 16th of April, we calculate the median for March, and on the 15th of and the 1st of May, we can calculate until the 15th of April. And then you see all this variability on top. This is Cabauw Tower. So this is Cabauw 207 meters, so the highest level of the tower. And you see that there is much more variability, which is by the median all filtered out. And you see this reflected as a quite modest, but still 20 ppm seasonal variability. So the idea of curve is to explain ICOS in one picture, or ICOS atmosphere in one picture. But that's easier said than done. I already showed you that you need a lot of more words when you go into the Curve app and you try to explain what is happening. But I think it's a good starting point for conversations when you have to explain about ICOS and what it's actually doing. You can use Curve and start simple. And if you want to explain more and explore more of this complex story, you can go in and show much more of the variability. You can show your own station. You can show how stations in in the mountains are different from a station in the land, or depending on the ecosystem, why stations in the north, in the far north, in the polar region have such a different signal from stations in the far south of the network, etc. So it really catches the millions of ICOS atmosphere data points in one picture and can boil it down to one final number, the atmospheric trend. So some numbers, we have 40 stations and we have 98 sampling levels in the time series. We have in total 357 time series, which extend back to 1972. And in total, this means that we have 31.8 million observation hours at the moment. And the Curve app demonstrates the quality of the ICOS data, as you can see, because we follow exactly the same trend up to a few ppm, tenth of ppm of the global network. We have the new real-time capabilities. We have our automated data pipelines because Curve is daily getting all the data, doing all the processing, which I will come to now, what is in there actually. And why we need this accuracy of the network over long time periods to be able to say something about the carbon cycle and the global greenhouse gas budgets, and why we need this network to do this. So, more words. CO2 and the greenhouse gases are really long-lived gases. So the signal that you see at the station is composed of contributions from many sources and sinks at many scales in time and space, where the atmosphere is working as an integrator. And what we do in the Curve app, we do a so-called Fourier analysis, where we separate all these signals by frequency, and a network of stations show different parts of that spectrum. We will show this more in detail. And if we want to really look into this global, regional, local levels, this is actually this regional, local level is where the climate carbon cycle wants information on and do the science. We cannot just look at the curve. We need models. We need to separate out background. We need to choose an averaging window and have a network which is at the right distance, and where we can, let's say, filter out the atmospheric noise, but also not too far apart so that transport model errors, which we need to be able to disentangle these signals, haven't taken over. And none of this will work when the underlying observations are accurate than less than this sub-ppm accuracy demand. And that should be over the whole of the network and continued for decades. So if we look a bit more in detail so on the top panel, you see here the concentrations at the tower. Sorry for that. And on top of that, we have this rising trend of the fossil fuel, which is caused by fossil fuel accumulation, partly compensated by uptake from the biosphere, which is a very low frequency varying signal. If we zoom into a 1 month of data, you see this in a tower like Cabauw Tower, you see this huge variability of more than 100 ppm. So you would say, we don't need a high accuracy. The signal is so big. We can live with 3, 4 ppm. Yes, for disentangling that signal, yes, but for the actual signal that we want to use in our model to translate from station to station the gradients, then the differences become very small. Only in the order of 1 to 2 ppm. So if you want to say something on that difference with some certainty, you need to have this difference measured within this 0.1 accurate. So not only precise, but also accurate. And this is in the lower panel, you see here how the variability of the signal is and where it's coming from, because in the night you see here this high rise of CO2, which is due to local CO2, respiration, fossil fuel emissions, and a very shallow boundary layer in which everything accumulates. And then in the morning, when the sun comes in, everything starts to be mixed into a thicker boundary layer, a thicker boundary layer, and this will get diluted. And actually, the current models cannot really resolve this stable boundary layer, so they will use the values from the daytime, which are, as you can see, also have less variability. But there is still, from day to day, there is this variability because of different transport directions, different sources and things seen in the path of the air that is measured by the station. So what is Fourier transform? So this is really, you can do a lot in Fourier transform to see which frequencies contribute to the signal. And for this example, this bird, when you listen to the bird, you will hear something which is then explained as a signal amplitude with time. You see some high frequencies variations, some slower frequencies, modulation of these higher and lower frequencies with time. And Fourier transform is translating everything to the domain from frequency versus amplitude, the power of, so this is how loud the tone is, and this is the frequency of the tones. And you can see that there are really sharp peaks. So this is actually what you hear as the bird sound. This is the modulations of the frequency, the singing up slower and faster, and some other higher and lower frequencies, which make that it sounds nice, because if it is only one frequency, it's a very not a very nice sound, but with these lower frequencies embedded, and you get a very nice sound. So also the atmosphere has this kind of frequencies and amplitudes, and this is a very complicated thing. But this is where we have the power spectrum for 4 actual ICOS stations. So here again, we have in a different frequency domain. So this goes from multi-year to to a day, to seconds. Here you see the power spectrum of the data. So we have this power spectrum data for the annual variability. We have the seasonal biosphere, and this is exactly what we are interested in, where we want to do our science on. We want to filter out this part, remove the background, remove all this higher frequency variability, and this is where the current models can use the information from our atmospheric signal. And all this is noise, let's say. So we have, for example, this diurnal variability gives a sharp peak. You can also see a background station. This station here is in Station North, is in Greenland. It doesn't have a lot of variability. All the lines are lower than the other stations, so there's less information or less density of the information. And for example, a station like Cabauw is far on top. It shows all this. It shows a higher signal, of course, from the biosphere and from the fossil fuel emissions. But on the other hand, there's also this big disturbing noise from the higher frequencies in as well. And so we have to look for the kind of middle ground that we get. We can remove this noise and look at the actual signal and make use of that for the different stations. So this is why we do this kind of Fourier transform and apply this also through models to remove that noise. So we have different in this panel. It's again a bit complicated, but it's to show you that over this, in the bottom line, this characteristic time scale, we have different spatial scale contributions. So we have traffic rush hour emissions. They pop up in this part of the time and space area. We have the diurnal biosphere and boundary layer signals. We have the synoptic weather patterns, the weekly anthropogenic cycle, and we have the seasonal biosphere, ocean uptake, and the fossil fuel trend. So all of these are by itself interesting signals, but we are limited by models and the measurement accuracy to look at only a few of these. So all the rest we have to take models and try to remove it as good as possible. So you can also see that for CO2, there's the complication. We don't only have emissions, we also have uptake. So the biosphere in winter is emitting, and in the summer it's taking up. We have the ocean, it's taking up, but that's only very slowly varying. And we have the fossil fuel signal, the blue line on top here, which is also varying, not in this picture, but it should be a bit more varying because depending on where you are, you have higher emissions in the winter when you use more fossil fuels and lower in the summer. But in this region, it's more or less the same. So we have this temporal variability, we have the spatial variability, and we have this signal from the from the atmosphere, which is hugely different when you have a background station or have a station like Cabauw, where you are in the middle of all these sources and sinks. And you can model this. This is how a model will then, the blue is the total CO2 concentration, the red is the contribution from fossil fuel, the green here is the uptake by the biosphere, and a very thin blue line here is the background. So this is the yearly signal as taken by the model. And when you are below that background, there's uptake. You can see also there's uptake here, and there's also emission at the same time going on. So this is what we have to tease out in the models. There's a little, so this is one example for Cabauw. You see here a peak in the night, and there's also a little peak in the uptake, which goes the other way, of course. It's negative. So the CO2 emissions and uptake are on this scale on the right. So if it's below the zero, there's uptake. And this signal is during the day, and it is maximum accumulated uptake contribution to CO2 by the end of the evening. And then we have again the respiration and the fossil fuel emissions taking over and giving a peak at night. So this example here, this peak, this was a peak where we have a very nice and narrow band where we have here Rotterdam, which has a high emission of fossil fuels. And here we have a pasture grassland with also a high uptake in this period in April, the early spring. And this is giving this rise to this high peak in uptake and then also the high peak in the CO2 emissions combined in this signal. So it's a lot of work, of course. So this is why you need a model. For every hour, you need to do this kind of analysis. Where is the air coming from? What sources and sinks did it see? How did they contribute? And then accumulate this, average this over a long period, and then try to update your emissions. That's the work we're going to do. So why do we need this high precision? If you have one station, you can do some trend uncertainty analysis on the data that we have, and then you will see that we need for one station time series up to 10 years or more before you get an uncertainty estimate for this annual trend of less than 0.25 per year, so less than 10%. And when we go to a station like Cabauw, and we have this annual seasonal cycle with an amplitude of about 2 ppm. This is about the trend. When we have an uncertainty of 0.1 ppm, this will introduce gradients, which will then in the models cause that these will be translated into emissions somewhere in the grid. It can be anywhere in the grid, spatial and in time. And this will give rise to errors which are in the same order of magnitude as the fluxes that we want to see. So that is why we really need this 0.1 ppm accuracy and also connected network compatibility between the different stations, because If you have less accuracy, this will destroy what you can do with the observations. So in another picture, here you see the different signals. We have the atmospheric background. This is on a logarithmic scale. So this is every step here is a factor of 10. So we have the atmospheric background, which is 400 ppm. We will remove this in the modeling as atmospheric background. We have the diurnal swing, which is the order of 25 ppm. For a lowland tower, we will average this and filter it out. Then we have the annual seasonal cycle, which is this yearly swing from summer to winter, which is about 80 ppm peak to peak. We will also model it and subtract it. Then we have the synoptic weather variability. That is, let's say, random noise, which we can filter out by averaging. So that is what we do. Then we have the annual growth rate, which is the global signal, which we are interested in. So that is why we also need this high precision. Then we have the regional signal, which is actually what we are interested in, interstational regional gradients of about 1 ppm when we average over a month. And this is what inversions will use to tell us more about the carbon cycle and the greenhouse gas budget. And this is on the same scale, this compatibility goal of WMO, 0.1 ppm. And this is what we achieve with the ICOS network repeatability. Which is part of this compatibility goal because there's also other parts of uncertainty. But in total, ICOS fulfills for the whole network this 0.1 ppm compatibility goal. Then we can see for each station, and I made here, you can look at these different contributions on different spatial temporal scales. You can look at the trend, the seasonal, the synoptic, diurnal, and the anthropogenic contributions at their different time scales. And you can see for each station from blue, where they capture it correctly because we measure it precise enough, until where we don't see that much of a signal. So we have to go back to this Fourier transform analysis and see how big is the the contribution for that frequency in the signal. And this is the kind of picture you get to. So you can see that most of the stations capture this trend, seasonal, and synoptic variability quite well. But then for the diurnal and the anthropogenic signal, it becomes a bit less, and some of them even are not very well suited for this diurnal and anthropogenic signal, especially for the background station, because and that is also why they were chosen to be like that, because they wanted to sample exactly these other signals and not so much be disturbed by the anthropogenic and diurnal signals. So this also reflects the design goals of the ICOS network. We want to have that information, but only when we can measure it correctly and when we can model it in complex situations like mountains. Our models are not really fit to do that yet, so we try to avoid that. So when we then look into the model uncertainties, these are much higher than this 0.1 ppm. At the moment, this uncertainty from transport models, depending on scale, global or regional or high resolutions, local, this uncertainty is 3 to 1 ppm on the CO2 scale. So when we add all these numbers up on these different uncertainties with the averaging window with time, so some of the errors are random errors, so by averaging we can average them out. Note please that this is again a logarithmic scale on both sides. Then you end up with an uncertainty which is the total model bias, which is dominating the total error. So at the moment with the models, we can go up to an uncertainty of about 1 ppm. And this also means that when we go for a one station, that we will get a signal to noise ratio of about 0.58 or an uncertainty of 1.7 ppm. And that depending on the averaging window and the distance from between stations, we can get more or less better signal. And our station should be in the middle of this region, this is a kind of composite. Every station will have a kind of a different landscape plot. But on the average for the whole ICOS network, it's something like this. So this means that we should have stations with a distance of about 200 to 300 kilometer distance. And we have the best signal from the stations on time periods of 1 week to up to 1 month. And this is the sweet spot. And this is exactly where, in fact, the ICOS network is. So if we are in this region, it means that we have only a few samples far away. That means that we have noise and signal are unfavorable. If we are here in this region, we are very close, and then the local plumes overwhelm the signal. If we are on this here, we have a long averaging time. We are very close, then the local sources contaminate. And if we have a long averaging time and we are far away, then the signal is diluted and the bias will add drifts or we get drifts from the bias. So there's also satellite observations, of course, and for satellite, you can give us a similar picture. So satellites will see a smaller signal. So in situ, we see 1 ppm for a regional network like ICOS. A satellite will see a signal in the total column atmosphere of about 1.1 or 0.2 ppm. The random measurement error, as showed, is this 0.05 to 0.1 ppm. A satellite will give a sounding random error of about 0.3. This is for the CO2M satellite, which Europe will launch starting next year. The current satellites are worse than that, but this is the design goal of this CO2M satellite. There is also a calibrated bias floor, which is 0.05 for in situ and 0.3 for the satellite, and only can achieve this 0.1 by using a reference bias correction based on in situ observations. The nice thing about satellites is, of course, that you get pictures of the whole globe. So over, let's say, every 3 years, every 3 days, you sample the whole globe. You get at 2 by 2 kilometer, you get observations when there is no clouds and not too much aerosol, and when there is no sea, because it only works best when you have land. But you get an almost global picture at a high resolution. One turnaround, you get a swath. The path over which you measure is 250 kilometers wide. So while in ICOS we only have 40 sites, and then you have to accumulate over time. While here, if there's not too much clouds and there is light, so you cannot go above 60 degrees north, for example, then you have good measurements. So the error because of the transport models is 1 to 3 ppm at the surface. For satellites, it's comparable, so that makes also that the signal to noise ratio is less favorable for satellites. Because you also have to take care of the vertical transport above the boundary layer and have to get that correct. It's more difficult to get this 1 to 3 ppm at the surface. So the signal to noise ratio in the end for the in situ is 20 to 500, but for the satellite it's 1 to 30, so it's almost a factor of 10 lower. And then, of course, why do we do these measurements if the models are not good enough? That is because the models should improve, and we really give the requirements for the modelers to improve their models and to do higher resolution and better corrections of the transport, especially in the boundary layer. And then this is the current situation. For the satellite, it's a bit like this. So here we have the relative scale. So this is the whether we can detect the CO2 signals in the atmosphere. 1 means we are fine, we do fine, and 0.05 is really not so good. So here for the satellite, we are getting some information at the moment with the current models. For ICOS, I think we are already quite well in the sweet spot. But when we look at the situation today, so we combine satellite and in situ. We see that in situ and satellite both can get some information, but when we can improve the transport model or by a factor of 10 in their predictions, then we go to a much better situation, and both are really in the sweet spot, and we can get also on a larger area a better signal and trust in our data that we can tease out the signals from fossil fuel sources and the biosphere. So coming to the conclusions, the curve application is a good starting point for conversations. It shows also that the ICOS atmosphere observation meet the compatibility goals for the major greenhouse gases. And this is really needed, and we can show that now by this analysis to perform carbon cycle science based on our observation and understand regional to global flux balances. All stations have their value within the network, so they all contribute with different information on different spatial and temporal scale. And ground-based observations are really critical to calibrate and validate satellite observations to reduce the biases which would otherwise make the observations more or less useless. Atmospheric transport models will need to evolve and improve, especially with regards to remove biases from atmospheric processes. And I already said, in fact, that satellite and ground-based observations are in principle complementary, but the ground-based observations are, let's say, essential. You cannot do without. And we cannot go back in time and measure. So in order to be able in the future to benefit from better models, analysis, and instrument satellites, we need the observations now. Thank you.
Thank you so much, Alex. That was a very comprehensive deep dive into this excellent tool that has been developed in Carbon Portal, and of course with the ICOS RI team. It is both relevant for scientists as well as for policymakers, and it's also resilient because we have not one station, we have 38 atmospheric stations. Thank you for that. There are some questions for you. I will take them from the top. Ladislav, would you like to ask your question about the legacy data that's gone in? Please feel free to unmute yourself and ask.
Hello, Alex. Thanks a lot for a very nice talk. I will just read what I wrote. I really like the graphics, and on the animation page, I just noticed that the ICOS network time series starts in the year 2000. So I assume this is merged data with historical site measurements.
Yes.
So could you just comment on the experience of merging the legacy data with the ICOS data? What were the challenges, or what did you encounter there? Thanks.
Yeah, so so merging this time series from pre-ICOS is really also the work from the same community. So we follow the same data processing routines, and this is really over the years we built up this capacity also at the Atmosphere Thematic Center to recalculate all this historic data, let's say. So when there is a scale update, also this in the annual releases of the ICOS data, we will also process for ICOS and even some non-ICOS stations. We will process all that data to make it really consistent and to avoid that we get this kind of biases in the data. Is that the answer, Ladislav?
Yeah, I guess fair enough. Thank you.
Thank you. Martin, do you have a comment about the trends? So it's about the units.
Well, it's very easy. I think slide number 2 or so, that one, the very first one where you see a couple of numbers on the top, it always worries me that the trend is given in ppm. As a scientist, it's trends need to be in mole fractions per time. And well, since I'm already on the mic, and it kind of follow up what Ladislav asked, more and more stations are being added to ICOS over time. And the newer stations tend to be kind of closer to the sources, while traditionally it was really a background network. And now, since models are getting better and we want to see more pollution, you have now 20 years of ICOS, the ICOS curve, and the newer years have more anthropogenically influenced stations. Then some climate skeptics could argue that the increase in the trend is favored by adding more polluted stations in more recent years. How do you respond to them? Or do you use the Fourier transform approach somehow to filter out the local pollution?
Yes, exactly. So all the higher frequencies go out, and you decompose the time series just by the seasonal cycle, and then also from that determine the trend by a fit. So yeah, this higher frequency is completely gone. And you can do an analysis, of course. You can leave these stations out and you will still see the same atmospheric trend. So we do this kind of analysis to get the uncertainty also of the estimate by taking one by one the stations out and see how the number changes, because this gives you an idea of the uncertainty of your estimate. And you can move them out, all of them. So you can take out 1, 2, 3, 4, etc., and repeat that in a Monte Carlo simulation, and that gives you a good impression on how robust your number is.
Yeah, okay, thank you. It's tricky because the number of stations changes over the 30 years you showed.
Yeah, exactly. But yeah, we take that into consideration when we calculate that number. Yeah. But your first question, yeah, that we do it in ppm per year, because that is actually what has been reported always, and that is what people understand. So, of course, we are scientists, but when we communicate with the general public or policymakers, we need to present it in such a way that people can actually understand it.
No, it reads just trend in ppm, and I would like to see a ppm per year.
Yeah, it's because it says it's the annual trend. So
yeah, well, but the trend is okay.
Yeah. We had long discussions on this already. Yes.
I mentioned that already earlier, but I thought it's another occasion to do that.
Okay, thank you.
If it's any consolation, Martin, I've also had the discussion with Alex. But yes, we have one last question from Mike about I think it's about the signal to noise plot. Would you like to ask it yourself?
Yeah, sure. I can do that. If you can hear me well, I will just proceed.
Yes.
Thanks, Alex. Excellent presentation and a lot of interesting stuff. Apart from all the trends, I actually wanted to ask you about the sweet spot plot, and the question you see in the chat. You kind of answered with your second to last slide, but can you give us a little bit more details? Have you evaluated or what kind of assumptions you did with the future performance of the models in that plot?
Yes, but I must admit it's a bit of hand waving, because I wanted to keep it simple, because if you do it for several stations, all will look a bit different. So I try to so I did the analysis for a kind of a average station. Yeah, so I've been working on a Jupyter notebook to do this analysis, so you can do it yourself and also make the plots and play with the parameters I used. So I think we will publish this in the Jupyter Hub, so that people can take this and play with it.
I really liked it, and I think, like, of course, and I trust you, and you know how to do this. I was just wondering, like, one would hope we would get even better with those models, especially for high resolutions of how they resolve. Yeah.
Mm-hmm.
And on this plot, I saw you kind of assumed that with the temporal variability, will still kind of stay in the same temporal ranges. So I was wondering about the technical details, but I guess I can look it up later. Thanks.
No. Okay.
Thank you. Yeah, maybe just a clarifying question from me. When you were showing the signal to noise landscape plots, were they for the composite ICOS stations, or were they for shown for individual stations, Alex?
And this is, in fact, for the second one was for the whole network, let's say.
Okay.
Yeah.
Okay.
Yeah.
Yeah.
The first one was more for one particular station. Yeah.
There are no more questions in the chat. If nobody has any more questions or comments, I would like to give a big round of applause to Alex for this very excellent talk on the ICOS curve. Please do look it up, an interactive tool, so I'm sure you'll have lots of interesting things from there. But thank you, Alex. Thank you all for being here. And so on behalf of the team, I'd welcome you in a month's time to the next ICOS Talks. Thank
Yes,
you.
and one more comment maybe from my side. While I was working on this, I think this would be nice material for a good paper to describe the atmosphere network and to make this point of that it's absolutely needed is 0.1 ppm, because there's many discussions on we can go to 0.3 or 0.5 or 1 ppm lower cost sensors, but I think we should make this argument that really this is at least for Europe and how complex the landscape is here, but it's probably everywhere in the world you would need this kind of compatibility goal for the observations if you want to use it.
Excellent point, Alex. So I think we will hear more from you about this, your emails. Thank you all for your time. Thank you for being here, and see you again later.